Okay, guys, welcome. Today we're going to talk about polynomials. What I want to be able to do specifically with that is I want to talk about a couple things. I want to talk about what the degree of a polynomial is. I want to talk about how we can do things algebraically with polynomials, such as adding, subtracting, multiplying, and dividing them. I also want to talk about what we mean when we say something is a factor of a polynomial, or what does a factorization of a polynomial mean, and also to be able to determine what's called end behavior of a polynomial. Okay, so first of all, what is a polynomial? First, we mean that you have this collection of terms that is essentially a collection of coefficients, so numbers times powers of x's. Now, and another thing that you have in polynomials is that each of these powers of x are positive whole numbers. So you don't have any fractional exponents or anything like that. Positive whole numbers. And of course, all those a0, a1, all the way through an are numbers, and they're usually called the coefficients. Now, we've already done an example of this. We've looked at quadratics. So we've looked at stuff like 3x squared plus x minus 2 or whatever. This is an example of a polynomial. Of course, you can attach more or less terms from it, right? And of course, linear functions are also polynomials. Their highest power is 1. You can attach higher exponents if you want. And of course, that's what we mean by a polynomial, sort of generalizing, adding powers of x. Okay, now the first thing I want to talk about is what's called the degree of a polynomial. Now, the degree of a polynomial is, in this case, we're going to say that it's degree n. Now, what does it mean to be degree n? Well, what's true about the n power here? Well, the degree of n, or specifically, I don't even need to say degree, we can just say that n is the highest power, and that's sort of the key. Whatever the highest power of x you see is, that's the degree of your polynomial. And we can sometimes say that that's degree of p, right, would be n, right? Or you could say degree of f if we're calling it f of x, something like that. And the second part here just sort of restates something I said on the previous slide. Those a0 through an, those are all considered coefficients. Those are just some numbers. Okay, so let's go through some examples. Now, what do we mean by an example of a polynomial with degree 0? Well, a polynomial of degree 0 means that we don't have any x terms, right? Or we have something like 3 times x to the 0, and that's our highest power. Well, we said that x to the 0 was just 1, so this is like y equals 3. So this is an example of a degree 1 polynomial, and of course its graph is a horizontal straight line. All right, so it's a horizontal line. Okay, now in part B, we could have something like polynomial of degree 1, so we could have something like y equals 2x plus 4, or something like that. Now, we talked about how we could graph something like this. This is just an example of a line, right? So we could plot our y-intercept. There are slopes too, so we could have something like this, right? So this is still a line, but it's no longer restricted to just be a horizontal line. It could be a line sort of with different slope, right? All right, so I guess we should say that it's a non-horizontal line, because if you have a horizontal line, then you're degree 0. Okay, part C is an example of our quadratic, right? So we have something like, so degree 2 means that we have something like y equals x squared plus 4 or something like that, right? And of course we can graph that. We know that this is going to be in a U shape, so it'll look something like that, okay? Now finally in part D, we want to graph something with degree 4, right? And they're going to ask us to use technology to do so. All right, so that's what I want to do here. So let me share the screen with a different program here. Okay, so let's go new share. And I want to share the calculator. Okay, so hopefully you can see that. So what I want to do now is I want to graph something that has degree 4. So I'm going to go to my y equals menu, and we'll do something like x. Let's see, x to the 4th minus let's do, oops, okay, 4, and then I need to get out of the exponent. And let's say minus a 3x to the 3rd, just to put some other terms in here. I can't do that again. I need to get out of the exponent, and we need to do a plus 5x squared minus an x and plus 1 or something. Keep doing that. Okay, let's get out of the exponent first. Plus x minus 1. Okay, and we'll hit graph and we'll see what happens. Now, let's make my window, let's zoom out a little bit just to see if anything else interesting is happening. And let's try graphing it now, because we should get some interesting happen. Let's maybe try, let's see, let's go window. Let's go zoom actually, and we'll go to zoom fit. So this is zoom 0 I'm doing. Now if we zoom fit, so okay, so still not much interesting is happening, but we get something like that. Now, what could potentially happen, and let's bring this back to the notes here. So let's go to new share and let's come back to the iPad. Okay, so let's try this again. Let's share it with the iPad. Okay, and we're back. Now, what can often happen with a degree 4 polynomial is something like this, all right, where you get some, and let's see, so I need one more. You could have something like this. All right, so you could have something more interesting, but in the example that we did, that didn't happen, but that's okay. Okay, so let's talk about how we can do some different things with adding, subtracting, and multiplying polynomials. Okay, so this sort of works, again, exactly like how you think it would. If you want to add two polynomials, this is where you combine like terms. And this is where you combine like terms, but first you distribute the negative. And then here is where you would do, so if you multiply, that's when you would use like your distributive property. Right. And when you do any of these things, you still have something that remains a polynomial. Now, in the next section, we'll talk about rational functions, and that's what would result when you divide two polynomials. Okay. So, of course, if you take two polynomials and you divide them, you not necessarily end up with a polynomial again. Okay. So here we're given these two polynomials, P and Q. And first we want to know what the degree of P and the degree of Q are. Well, the degree is just the highest exponent. So if we look at p, it looks like our highest exponent is 3. So that's the degree of p. And the degree of q looks like, again, the highest exponent there is 3. Okay. And in part C, we want to add these two things. So p plus q of x is going to be 2 minus 7x squared plus 5x to the third. And then q, I have a 1, and then I have a 9x plus x squared plus 5x to the third. So if I combine like terms, I'm going to get a 3, I'm going to get a 9x, I'm going to get a minus 6x squared, and a 10x to the third. So that's what happens when I add them. All right, now the degree of this has degree also equal to 3, because my highest exponent is still 3. Now, we want to find the difference. We want to find p of x minus q of x. Now here you have to be careful. You have to remember to distribute. So you have 2 minus 7x squared plus 5x to the third, and I'm subtracting 1 plus 9x plus x squared plus 5x to the third. So when I distribute that negative, I'm going to have 2 minus 7x squared plus 5x to the third. And I'm going to have a minus 1 minus 9x minus x squared and a minus 5x to the third. And now if I combine those like terms, 2 minus 1 is 1. And then I have a minus 9x. And then a minus 7x minus x squared is minus 8x squared. And 5x to the third minus 5x to the third just cancels. So in this case, I'm left with 1 minus 9x minus 8x squared. And this has degree only equal to 2. Right? Because we lost that x to the third term there. All right, so here your degree is only 2. Okay. Now, this sort of highlights what happens when you add two polynomials, what happens to the degree. Basically, what happens is that whatever the maximum degree is, your degree is always going to be less than or equal to when you add them, because of the fact that you could get that cancellation of the highest power, all right, or multiple powers at that, right? So it's always going to be less than or equal to whatever your biggest power is, right, regardless if you're adding or subtracting. Okay, now let's look at one where we multiply. So now in example 3, our degree of our p polynomial is 2, because my highest exponent is 2. And the degree of my q looks like is 5. Okay, so that's the first part. And now I want to find p times q, all right, or p of x times q of x. So in this case, I want to multiply 2 minus 3x squared times 4x plus 7x to the 5th. So if I distribute here, I'm going to get an 8x plus a 14x to the 5th minus a 12x to the 3rd, and then it looks like a minus 21x to the 7th. All right, so it looks like here my degree is 7 now. All right, so now how does that relate when we multiply? What happens there? If we multiply two polynomials, then we add the degrees of each to get the new degree, right? See, before our degree of p was 2, degree of q was 5, and we add them, we get 7, which is the degree of what happens when we multiply p and q together. Okay. Now, the next thing that we need to talk about is what we mean by what's called a zero of a polynomial and the factorization of a polynomial. Now, we say that a number is a zero of a polynomial if plugging it in produces 0, right? So in English, this means plugging in gives 0. Right? So that's what we mean when we have a 0. So for example, if you look at x squared minus 5x plus 6, 2 is a 0, because if you plug 2 into this thing, you get 4 minus 10 plus 6, which is 0. right? And the same thing would happen for plugging in 3. All right, so sometimes you can also use the words roots to mean the same thing as 0. All right, so all we mean by a root or a 0 of a polynomial is that if we plug that number in, the result is 0. Okay, now in example 4, we want to explain why p of x is equal to x squared plus 1 has no real zeros. Of course, this is something that we've talked about before. We want to find when is 0 equal to x squared plus 1. And of course, you have a problem because you get x squared is equal to -1, which means that x is equal to plus or minus square root of -1. But this is undefined, which means that this equation has no x solutions. So of course, there's no real zeros. All right, so that's sort of why x squared plus 1 has no real zeros. Okay. Now, the next thing that we can talk about is we say a factor of a polynomial. Okay. Now, all we mean by a factor of a polynomial is that we can write, so a factor of a polynomial. And here we're calling it x minus t, but a factor of a polynomial is really just any, even just g is also a factor. Right? So if you can write your original polynomial as something times something else, or even something times the same something, each of these things are considered factors. All right, and this goes back to when you learned in elementary school, you have that two numbers, if you multiply them together, each of those numbers are factors, and the result is the product, right? So sort of same logic there. Okay, so here, of course, x minus 2 is a factor, x minus 5 is a factor, and really x squared plus 1 is also a factor. All right, but according to this book's definition, we can write our original polynomial is x minus 2 times something else, so it's a factor. And we can write our polynomial as x minus 5 times something else, so it is a factor. Now in part C, we want to show that 2 and 5 are zeros RP. So show 2 is a 0 first. Well, this is a 0 because if I plug in 2, I get 2 minus 2, 2 minus 5, 4 plus 1, which is a 0 times -3 times 5, but 0 times anything is just 0. So that's a 0. And of course, 5 is also, because we'll get 3 times 0 plus 26, and this is just 0. Now, of course, these are the only real ones because if you look at the other factor, if you look at x squared plus 1, we said that this has no zeros. So the only zeros are going to come from the other factors, which are the 2 and the 5. So of course, 2 and 5 are the only zeros. Okay, so that's a little bit more about factoring in zeros. All right, now of course the relationship between this is that you have, if you have a polynomial p, and I guess in this case we're using t, so I should say p of t. So p of t is a polynomial. Then you have that t is a 0 if and only if x minus t is a factor of p. Right? And of course, if you plug in t in for x, that would make this 0. So that needs to be true in order for t to be a 0 of your polynomial. Okay. Now, one thing that we can say about the number of zeros for a particular polynomial is that the number of roots or the number of zeros at most is whatever its degree is. So for example, a degree n polynomial has at most n zeros. All right, that's really what this is saying. So if you have a, and we talked about this, right, with a quadratic function, right? So the degree of a quadratic function is 2, and we saw the 3 different scenarios that you can have. You can either have 2, 1, or 0, which of course is at most 2. Okay. So now the last thing that we can talk about here is sort of what's called this end behavior, all right, or behavior as we go towards either x is positive or negative infinity. So we're letting p be defined by this polynomial, this x to the 5th minus 99,999x to the 4th minus 9,999x to the 3rd minus 999x squared minus 99x minus 9. Okay, so we want to know, is this polynomial positive or negative when x is very, very, very large? Well, if x is large, then x to the 5th is going to be much larger than x to the 4th, x to the 3rd, x squared, x, and any constants, right? So what this aims to really show is that after a while, x to the 5th is really the only term that matters. So x to the 5th really dictates the behavior. So even though the coefficients of all those other terms are large negative numbers, it doesn't matter because you can just make x larger and larger until it doesn't matter anymore. So x to the 5th dictates behavior. So if x is very large, then of course p of x is positive. All right, and that's the idea, is that no matter how gross these coefficients of the lesser terms are, if you're approaching infinity, they don't matter because they're the lower order terms. Right? So what we do is, in order to determine the behavior of a polynomial near infinity or negative infinity, we essentially are just looking at the term with the highest degree. Right? And what happens is that if you look at that term with the highest degree, the polynomial behaves like that highest term. So you can sort of take this a step further, and if you look at whether the degree is even or odd, and if the leading coefficient is positive or negative, you can come up with a simple example of each of those cases, right? So you could, for example, look at y equals x, y equals negative x, y equals x squared, or y equals negative x squared. And whatever happens to those simple functions has to also happen for your complicated function. And of course, your end behavior is always one of these 4 options, right? So as you move to the left, you'll either go up or down. As you move to the right, you'll either go up or down. And that's sort of the idea. Okay, so let's look at an example here. Well, let me go back because there isn't an example here. So let me just sort of add one in here. Let's suppose we wanted to look at something like the end behavior of f of x is, let's say, 5x to the 15th plus 4, something like that. Okay, well, we know that if we look at the term with the highest degree, that's going to tell the story, right? So we need to look at this 5x to the 15th. Now, you might not know off the top of your head how this is going to behave, but what we can do is let's look at the degree. All right, is it even or odd? Well, 15 is odd, so of course it's odd. Let's look at the leading coefficient. Is it positive or negative? It's 5, which of course is positive. So now what's the easiest example of an odd degree, that would be x to the first, right? 1 is the easiest odd number. What's the easiest positive coefficient we could have? That would be a positive 1. And of course, if you simplify this, this is y equals x. Now, if you look at the graph of y equals x, it looks something like this. And as you move to the right, it goes up. As you move to the left, it goes down. So since that happens for this function, that must also happen for this. So what we could say is as x increases, y increases, and as x decreases, y also decreases. And that's sort of the idea. And you could, of course, if your degree is even, then you just look at x squared. And if your leading coefficient is negative instead of 1, you would use -1. And you could look at that graph. Okay. Next example. So we want to look at the polynomial x to the 5th plus x squared minus 1. And we want to explain why p has a 0 in the interval 0 to 1. Okay. Now the idea here is look at p of 0. If you plug in 0, you get 0 to the 5th plus 0 squared minus 1. So we get a -1. If we look at p of 1, we get 1 to the 5th plus 1 squared minus 1, which is positive 1. So in a graphical sense, when p is 0, we're at -1. And when x is 1, sorry, when x is 0, we get -1. When x is 1, p is positive 1. Now, polynomials are continuous. So those two lines those 2 points have to be connected by a curve, right? And if that happens, that means that you have to cross over 0 at some point. So that's sort of the reasoning there, right? And this is typically called the intermediate value theorem, but this essentially says that if you have a polynomial and you know a spot where it's positive and a spot where it's negative, then that means that you had to have crossed 0 at some point between those two x values, right? So that's what we mean by that. Now, one thing that you can say about a polynomial with odd degree is that there's at least one real 0. Because for odd degree, you're either going to behave like this or you're going to behave like that, right? So you're going to either decrease and increase or increase, decrease. So that means that at some point you have to pass 0 at least one time, right? You can't skip over it. Okay, now the last thing that we're going to do is we're going to return to a calculator example. We're going to look at this function and we're going to do so on the calculator. So let me go ahead and bring that up. So let's do a new share. And I want to bring up the calculator. Okay, so now we have the calculator up. So I want to look at this function. So let me clear this out. And we want to look at x to the 4th minus 4x to the 3rd minus 2x squared. Okay, let's pretend that I know how to do this. So let's go x to the 4th, and I got to remember that I need to get out of the exponent. Minus 4x to the 3rd out of the exponent minus 2x squared and then I need plus 13x and a plus 12. Okay, we'll enter that in and we'll graph it. All right, now let's maybe zoom out a little bit. Let's do zoom and fit again so we can get a good idea of what's happening. Now, I'm not really seeing too much action here, but maybe if we zoom in, we'll be able to find it. So let's go and zoom back in. Let's maybe do a zoom from, let's see, I want to do window, and let's do something like -5 to 5. Let's try that and see if that's any better. And then we'll graph it. And then let's do zoom fit again. Okay, so it's a little bit better, but let's bring it in even closer. So let's go window. Let's try maybe -3 to 4. All right, so a lot of this finding an appropriate window is really more of an art form than an exact science. So you just have to be patient with it. So let's do zoom 0. Okay, and now we can sort of see that we are getting some interesting behavior, right? So we're getting sort of a minimum occurring. Looks like at -1, we get a little peak there at x equals 1, and then another little minimum here at x equals 3, it looks like. All right, so we can maybe say that the interval that would be a good job of showing what's happening here would be something like x equals -3 to x equals 4. All right, so that would be fine here. All right, but that concludes this video on polynomials. I hope you enjoyed, and I will see you next time.